The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. This is Mary. We'll be getting started here in just 1 minute. I've got all 8 of our CIGLR Summer Fellows here, and they're excited to tell you about their summer research. Okay, so it is 9 o'clock. We will go ahead and get started. We are going to be keeping on time this morning. The fellows will each present for 15 minutes. We'll have a 5-minute question and answer session. We ask that if you have a question, you may either type it in the chat box or you can use the raise hand feature in the webinar system, and Aubrey Lashway and I will be handling the question and answer and relaying those questions to the fellows. I want to thank all the fellows for joining us this summer. Certainly unusual circumstances, I'm sure a summer that none of us are going to forget, but I really commend them for their open-mindedness and willingness to participate in this virtual program when at the outset we weren't quite sure how well it was going to go, but I think everybody made the best of the situation, and we certainly loved interacting with them and having them with us for the summer. They did a fantastic job, and we're just very impressive with their professionalism and how hard they worked. And likewise, the mentors, thank you so much for your time and dedication. I know that many of you met with your fellows daily, and that's on top of an already really challenging year for everybody that's trying to work out field and lab work under these trying times. So thank you so much. And also thank you to the CIGLR team who worked so hard to make sure that this was a great experience for the fellows. Michelle Wensman hosted, I think, more than 19 different events with the fellows all summer long. So thank you so much to Michelle for that. And Aubrey worked with them on creating videos virtually that will help show off their fellowship. So thanks to everybody who participated. I think we can all feel really good about how things went this summer. So with that, I'm going to turn it over to Chance Ford, who will give us our first presentation. He worked on a project with Lauren Fry, Lacey Mason, Brent Lofgren, Lindsay Fitzpatrick, and Yao Hu. So Chance, it's all yours.
All right. Can you hear me all right, Mary?
Yeah, we can hear you.
Great. So my name is Chance. I'm a PhD candidate at the Hydrogeology Lab at Michigan State. And this summer I worked on the Runoff Risk Tools project. So first I'll just give you a little introduction to the project and what the overall project goals are. And then I'll get into how I've been, what I've been doing this summer to contribute. Before finally ending on what's next for me in the project. So the Runoff Risk Tools project, the overall objective is to develop an online tool that allows farmers or other members of the public to assess runoff risk forecasts in their area. And the significance of this is to try and reduce agricultural nutrient runoff. As I'm sure most people here in the Great Lakes are familiar, nutrient runoff from farm fields that gets into surface waters leads to ultimately the lakes, and that can lead to these harmful algal blooms we see in the summer, like the figure on the right. And so this tool is designed to allow people to, again, forecast runoff so that, say, a farmer can look at their field and say, okay, we have a high runoff risk on Wednesday, so I'll wait to apply my fertilizers on Thursday and hopefully reduce the amount of that nutrient getting into surface waters. And this tool is designed off of outputs from the National Water Model, and that's a distributed simulation model of surface flows across the continental United States. So you can see here on this bottom figure on the right, this is outputs of stream flow from the National Water Model. This is from Wednesday across the continental United States. This is from the National Water Model map tool of OWP at the website listed. However, the National Water Model spatial resolution ranges from 250-meter grid cells up to 1 kilometer. And for the targeted kind of runoff risk that we want for farm fields, it needs to have better resolution or higher resolution than what it currently has. And so to address that, one of the modelers in this project group, Dr. Yao Hu, has been developing a statistical model which takes outputs from the National Water Model, as well as observed point data from several sources, and combines those to assess runoff risk in a targeted field scale. So those observational point data that go into this from 104 different sites, and those are the points here on the map. They're spread out across 7 different states in the Great Lakes Basin, and they're across 14 different domains, and that's those yellow boxes you see here on the map. Data ranges from about 2002 to 2018, and these are sites that are located at the edge of farm fields, hence edge of field, that are instrumented to collect measurements of surface runoff values at the edges of those fields. So the statistical model takes the National Water Model outputs as well as this observational data and then combines them to assess runoff risk. However, as you saw from the map, the spatial spread or the distribution of these EOF sites is somewhat limited. And so there needs to be a way to apply the statistical model to a larger area, including areas that don't have this observational data. And that's where I come into this project. This summer has been developing this regionalization approach so that way we can take these different outputs, both observed and modeled, run the statistical model, and then regionalize that and apply that to larger and larger areas that don't have that observational data, ultimately leading to coverage over the continental United States. And so how we've gone about doing this is to really identify groupings of watersheds with similar runoff responses. And so we've been doing that through an unsupervised clustering analysis, specifically through principal component analysis, or PCA, and KMeans. And I'll get into a moment what that means. But as kind of a broad overview of my actual process for this project, the first step for me is to create spatial aggregates across HUC-10 watersheds. So I take things that are related to runoff, whether they're drivers such as precip, or indirect influences such as topography and soil content, and I spatially aggregate those across HUC-10 watersheds. And then I take those spatial aggregates and run the principal component analysis on those. And what the principal component analysis does is that large data set identifies variables, or what's known as components, within that data set that are responsible for variations within the overall data. And so then those components, they reduce the dimensionality of the data so that you can start to compare data that maybe have different units or different scales. And so then taking those components, we run those through the K-means. And so with that reduced dimensionality from the PCA, K-means then takes those HUC-10s and clusters them into groups with very similar responses. And so these clusters then are what gives us the basis for the regionalization approach. Now, this was developed with the Dubé domain in mind. The Dubé is this red box here in the map. And we focused on one domain rather than the 14, mainly just because of technical limitations. Probably the biggest hurdle for me this summer has been with working remotely, not having direct access to the data. And a lot of these gridded model outputs are very large file sizes that makes it not very feasible to transfer them remotely. We actually ended up having to do a physical hard drive handoff at one point just so I could get enough data to start working on this. And so with that hard drive, I was able to get 3 years of data for the Dubé, so 2006, 2010, and 2011. And the reason we chose the Dubé is because it's relatively large compared to some of the other EOF sites or EOF domains. And also it stretches north to south along Wisconsin. And so it covers a wide variety of topography and geology. And hopefully that landscape variety will help in applying this regionalization to other areas. So as I mentioned, the first step in this process for me has been the spatial aggregations. So I take something like what we see here on the left with the gridded output from the National Water Model. So in this case, this is annual melt for the Dubé domain, 2006. These gridded outputs, hourly time steps. So first I take annual statistics from those hourly time steps, and then I take that annual grid and I overlay those HUC-10 polygons that we see here in the middle. And those are the HUC-10s that are completely contained within the Dubé domain. And then for each of those watersheds, I extract the mean value of those grid cells within the HUC-10. And that gives us something like we see here on the right, where then we have this average annual value, in this case of melt, for each of those HUC-10s within the domain. And so I do this for quite a few different variables. As I said, anything that seems like it may have an influence either directly or indirectly on runoff generation. So obviously the drivers of runoff, things like rain, both the amount and the rate, SWE, melt, those sorts of things that are actually driving the runoff are included, as well as indirect influences such as from the landscape and the geology, such as depth of bedrock or soil composition and those sorts of things. And there are a few other variables that you'll notice here that are in gray. Those are things that are going to be included but have not, but these are things relating to actual stream flow characteristics in the region, irrigated area, those sorts of things. So once I have all of these different variables aggregated across HUC10s, I put them all into one large data frame, and then I take that data frame of HUC10 values and I run the principal component analysis on it. And so the principal component analysis gives us something like this figure we see here on the right, where the x-axis is individual components. And so in this case, this goes up to 34. And then the y-axis is variances. And you can think of this as how much of the data set's variability is described by this component. And so visually looking at this figure, we can see a large part of that data set's variability is described by component 1, in this case, 45% of it. Now, the PCA will give you as many components as you want, but as you get further to the right on this graph, as you get more and more components, those components become less and less useful because they get closer and closer to 0. So the rule of thumb generally is you want to include enough components that 85% or more of data set variability is described. So in our case, that ended up being 8 components, which is where that vertical line is drawn. And so those 8 components describe 86% of our overall data set variability. And the more variability that's described by these components, the larger influence that component's going to have on the clustering and ultimately then on the regionalization. And we can start to dig into what's driving these components. What are the differences between these different components from the PCA? And so this plot here on the left, this is comparing component 1 and component 2, which is those two are our largest descriptors of variability within the data set. And so in this case, the x-axis is component 1 and the y-axis is component 2. And so then these vectors are those different variables. And the longer that vector is in a particular direction, the more influential it is for that component. So for component 1, we can see things like, our sand terms over here are very influential, and sand 1, 2, 3, 4, those are just different depths of sand, different layers. And in the opposite direction, we see our clay terms come out. And even though they're in opposite directions, they're both still on the x-axis, and they're both influential, but just in opposite directions, because obviously as you have more sand in the soil, you have less clay and vice versa. And the second component, we see other terms start to come out as influential, other variables, things like our vegetation extent, our land cover terms like grassland and other things. And then we start to see some influence on both our soil moisture terms up here, our elevation. Those are important to both of these components. But we can actually look at how the HUC10 values map out on these dimensions. So again, these are the same dimensions. X-axis is component 1, y-axis is component 2, and then the points are then the actual individual HUC10s and how they map on these dimensions. And so just looking at this visually, we can already start to see some grouping starting to form, right? We have this pretty tight cluster over on the left in blue. We have another grouping up top in this green, and then a more spread out kind of grouping forming down in the bottom. But obviously this visual kind of grouping isn't very scientific, and also keep in mind that this is only 2 out of 8 components. So this is 2 out of 8 dimensions, and it's difficult to try and visualize 8 dimensions, and that's where KMeans comes in. KMeans then takes these 8 different dimensions and how these HUC10 values plot on those 8 dimensions, and then it clusters them based on how close they are within those dimensions. And so using KMeans, then we come up with these different clusters. So this bottom left figure is what we were just looking at. Those are those HUC10 values plotted on the first 2 components. And then the right figure is the actual outputs from KMeans and the clusters. And this is the same diagram in the sense that x-axis is the first component and y-axis is the second component. But now we see these different colors and these polygons indicating the different clusters of the data. And so you see that, our initial groupings, there are some groupings off on the left, but because there are more clusters than just 3, we're starting to see some differences come out. Now it seems a little confusing because you do notice some overlap of these polygons, but again, keep in mind this is because of that we're only looking at 2 of those 8 dimensions. So if we are able to visualize all 8 dimensions at once, that overlap wouldn't necessarily be there. But so now that we have our clusters, we can actually start to map these out and see what they look like spatially. So this figure here on the right then is the HUC-10s identified by their clusters from KMeans. The points on this map are just the EOF sites located within the bay. And looking at this spatially, we can see that generally the clusters seem to stick close together. I mean, there are some exceptions. Cluster 7's pretty spread out across the region. Cluster 5's got some spatial variability north to south, but generally they group somewhat together. Now, of our 8 clusters that contain EOF 1, 2, and a little bit pretty diverse in their variables. For instance, cluster 6 contains Madison, and so it's got a very high percentage of urban land cover compared to the other clusters, and there are other differences in those variables, whether it's precip or land cover. And this is good news for the regionalization approach, because the more variability we can capture within those EOF clusters, the more applicable this is going to be going forward over larger areas. So obviously, based on those results, this isn't finished for me, so I'm actually going to continue to work on this project to a degree this fall after the Summer Fellows has ended. And so the first step for me then is, if you recall those variables that were in gray that had yet to be included in this analysis, I need to spatially aggregate those and include those in the data frame and then rerun it to see if that changes the cluster. And then the next step is a sensitivity analysis of this. So what happens if we change the amount of clusters that we involve, different iterations, those sorts of things. And then this all needs to be tied back around to the statistical model. So once we have this regionalization approach, it needs to be implemented into the statistical model so that Dr. Hu can then apply that to other areas. And then ultimately then this needs to be expanded. So the first step would be to expand this to the other 13 EOF domains, before ultimately expanding this to larger and larger areas, eventually applying it to CONUS. So I've had quite a bit of help this summer in getting this project going. First and foremost, I want to thank the Summer Fellows Program for the opportunity to work on this project this summer. I also want to thank the Runoff Risk Tools team. Anything that I needed, whether it's interpreting results, to getting code to run, to handing off hard drives, everyone was always very willing to help me, and I really appreciate it. And then we also had some help from folks at the National Water Model and getting regionalization variables or understanding the model outputs and those sorts of things. So I'm grateful to everyone for their help this summer. So here are some of my references, and I'll take any questions.
Wonderful. Thank you so much, Chance. If anyone has a question, please type it into the question or chat box, or you may also raise your hand and we'll call on you. Greg Lang says, wow, great talk, well done. Lauren Fry, great job, Chance. Really enjoyed working with you on this over the summer, and I'm looking forward to continuing the project with you this fall. What you developed is a key component to the transition of the runoff risk model operations, exclamation point. Thank you so much for that comment, Lauren. I'm glad to hear it. I'm sure Chance is too.
Yes, thank you, Lauren.
I'm excited to hear that you're going to be continuing to work on it a bit over the fall too, Chance. That's really fantastic.
Yeah, no, I've really enjoyed working on this project. It's been really interesting, and it's been great getting to know everyone on the team.
Okay. Any other questions or comments for Chance? I'll just pause a second here in case someone's typing. Okay. I don't see anything else coming in, so I'm going to go ahead, Chance, and have you turn off your webcam.